Okay, today we are going to talk about the next two sections of Chapter 9. We're going to talk about reflections and rotations. Now, yesterday we talked about vectors and we talked about translations. We did revisit a little bit about transformations in general, but not too much. The really big thing that we did talk about yesterday were our use of the terms vectors, matrices, and of course isometries. This is two sections, but I think that you'll agree with me after we get through this, it's a fairly simple set. The first thing that we need to revisit is a couple of things about reflections. And we just always like to kind of remember what it is that we knew about reflections, because nothing's really changed about reflections from Chapter 4 or October till now. If we are reflecting something, we're mirroring an object about or over a line of reflection. Technically, we call this about a line of reflection, but really we're mirroring it over something. It is an isometry. Back in Chapter 4, remember we talked about them being congruence transformations. We defined yesterday the term isometry as, well, just a fancy word for a congruence transformation. So we know that an isometry does include reflections. The other thing that we talked about in Chapter 4, and these are old notes, if you want to recopy them, you're welcome to, but you don't have to. When we talked about reflections back in the day, we talked about a reflection over the x-axis or reflection over the y-axis. So if I look at this, I have the point AB, and if I reflect it over the x-axis, remember I negate the y, so the point AB becomes a negative b. If I am going to reflect over the y-axis, the point AB becomes negative AB. And we talked about the fact that it was just kind of interesting that if we're we're reflecting over the x, we negate the y. If we are reflecting over the y, we negate the x. Now, that's what we talked about, or that was the extent of what we talked about with reflections in Chapter 4. For Chapter 9, though, we do need to talk about reflections in a different way. We do need to talk about reflections over, well, any line, and we'll have some specifics for it, and then we'll also talk about how we can reflect over the line y is equal to x. Now, we're going to spend some time in GeoGebra to get us to a good place with this material. Okay. So, excuse me here, turn those on. Alright, so let's say I go in and I have some object, right, and I'm going to start over here. Alright, I have some point that is going to be out in space, and I'm just going to choose a point right here. Okay? And we should see that that point is 1, 4. Now, if I reflect it over the x-axis, that's a line. That's this line here. Excuse me, this line here. But let's say I wanted to change that. And instead of reflecting over an axis, let's move that line up 2 units. Right? So I'm going to take that and say, well, this is my line of reflection. Well, I have a nice little reflect tool here. So I'm going to reflect that object over this. Now, a couple of nice things about GeoGebra is it does use our terminology here, so this new point is A prime. But let's take a look at our coordinates. We have 1, 4, and 1, 0. Well, why is it 1, 0? If it was 1, 4, I reflected it over this line. It goes to here. Well, how far or how many units away is A from this line? 2 units, right? So that means that if I'm going to reflect it on the other side, it's got to go how many units on the other side? 2. 2. All right, so if I'm going to reflect about any line, especially one that is horizontal, that means that the distance from here to here has to be the same as the distance from there to there. And that makes sense. Let's see what happens if I move my point up. Let's say I take this point and I move that whole line up 1 unit. So now I have this horizontal line, y is equal to 3. Well, it was 1 unit away here, 1 unit away there. That makes sense. Well, let's see what happens if I were to take this and make it a vertical line. Let's see, I have 1, 4, I have 7, 4. 3 units away, 3 units away. So if I'm reflecting over a horizontal or a vertical line, all I'm doing is seeing how far away from that line my object is. And this works for a point, this works for any object that I may have. Just for the sake of argument, let's put a little triangle in here. And let's say I wanted to reflect that object over my line. Well, you should notice that point E was about 2 units away, about 2 units away. Of course, A and A prime are the same. And here I have 3 units away this direction, 3 units away that direction. Everyone see that? We're going through and we're just seeing how far away from our line of reflection that is?
Yeah.
All right. Now, one thing I'll tell you about this. Can you go through, or can we go through and come up with some sort of algebraic means of expressing a reflection in kind of real space and in terms of x's and y's and this and that? Yeah. Is it more often than not just as easy to go in and say, hey, you know what? This point is 3 units away. Well, I'm going to go 3 units this way? Yes. That's almost always going to be easier for us. And I really urge you to use that to your advantage when we're talking about reflecting over a vertical line or a horizontal line. The other thing we should probably revisit is our equations of horizontal and vertical lines. Remember, a vertical line is of the form x is equal to a number, and then a horizontal line is of the form y is equal to a number. All right, so good with that. All right. All right, well, let's take a look at one other different kind of line. Let's say, instead of dealing with a vertical line or a horizontal line, I put in this line. First and foremost, what's the equation of that line? What's the equation of the line I'm reflecting over? Well, it goes through 0, 0, so that's what its y-intercept is. Okay, so it's got a slope of 1, and it goes through 0, 0. So that means that y is equal to my m, which is 1, x plus b, which is 0. So the equation of this line is y equals x. Okay. All right, so if I'm reflecting over the line y is equal to x, let's take a look at what happens to my coordinates. I know that there's a distance from here to here that's got to be the same as the distance from there to there. But immediately we're dealing with some issues, right? Now, arguably, if I wanted to, I have an equation of this line. I have this point. I can figure out what the slope of the perpendicular line would be, or the line what we call normal, and figure out the distance from here to there after I figure out that point of intersection. Doable. And then I could figure out that distance that way. But when Descartes set up this Cartesian coordinate system, there were some things that it afforded us. And looking at the coordinates is probably the best one. Because let's see. I'm reflecting over the line y is equal to x. My original point, A, was at 1, 4. My new point, 4, 1. What happened? I had 1, 4, and now I have 4, 1. What occurred? What happened to the x's and y's? They just switched places, right? So if I'm going to take a point and I'm going to reflect it over the line y is equal to x, I'm just going to invert the coordinates. Well, let's look at what happens. Similarly, if I reflect over the line y is equal to negative x. Let's see what we have here. I had 1, 4. Now I have
-4, -1. They just split and then become negative?
That's exactly right. Okay. So I have a very quick and easy way of talking about reflections, especially when we talk about it in terms of our y's and x's. Right? So let's recap that. So if I'm going to reflect over any vertical or horizontal line, I just determine that distance and then go the opposite direction. But formulaically, if I'm going to reflect over the line y is equal to x, my x's and y's just shift. If I'm going to reflect over the line y is equal to negative x, well, they invert or switch and negate. So let's do a quick example here. Let's say I gave you these points, A, B, and C. Actually, we'll just do A and B. I've got 2, 3, and we'll do an easy one of 1, -4. Okay. Now, if I want to take those points and I want to reflect them over the line y is equal to x, that means that my x's and y's are just going to change. So my new point is 3, 2, and my new point is 4, 1. If I want to reflect over the line y is equal to negative x, well, they're going to switch and negate. So 2, 3 becomes -3, -2, and 1, 4 becomes -4, -1. Now this is a really nice result because this allows me to very quickly and easily get to an answer. Allows me to quickly and easily get to what my new coordinates will be. Yesterday we talked about the idea of being able to do some sort of transformation on a mass scale. If we have this, that's a pretty easy transformation for us to do. If I was writing code, I could write this pretty quickly. Now, one thing that I do want to show you, and I'm really just going to show you because the book takes some time to do this, we can go through and do some reflections with a matrix. Right? So, and I would tell you that I'm just going to show you this. I wouldn't worry too much about getting it into your notes, but I just want you, when you see it in the book, to understand where this is coming from. So if I wanted to reflect over the x-axis, right, and I had a series of points, and I'm going to put these in matrix format. 1, 2, and 3, 4. If I wanted to use matrix multiplication, or excuse me, use matrices to reflect them, I can, and I do it using what we call matrix multiplication. And I multiply it by what we call our x inversion, or x-axis inversion matrix. Now, matrix multiplication is not quite as simple as taking 1 times 1 and 3 times 0. Instead, what we're actually doing is going through and taking our columns times a row and then putting that answer right there. Okay, so let me show you what that would look like if I worked it out. Okay. So to get this first coordinate, I'm going to take, and we should probably check, write down where we're going with this. We know that this is going to end up being 1, -2, and then 3, -4, right? All right, so I'm going to take my first coordinates, 1, 2, and I'm going to multiply it by 1, 0. So that means 1 times 1 plus 2 times 0. I'm then going to take the same thing, 1, 3, and I'm going to multiply it by, or excuse me, not 1, 3, 1, 2, and I'm going to multiply it down here. All right, so that's going to be 1 times 0, plus 2 times negative 1. Now, this is how matrix multiplication works. I don't really want to get into why it works this way at this point, because you will spend considerable time in algebra doing it. But this is more just kind of you understanding that it's possible. Is that your question?
Oh, I was going to say, why do you plus 2 instead of telling me about this?
Because basically what I'm doing is I'm doing lots of what we call scalar multiplications at once.
Okay.
And the actual proof of this involves lots of those little scalars put together, and then you see a bunch of them drop out, and then you're just adding up the components.
Okay.
So it's a good question, though. To get this coordinate, I'm going to take 3, 4, multiply it here, so that's going to be 3 times 1 plus 4 times 0. And then same thing here, 3, 4, multiplied here. So that's going to be 3 times 0 plus 4 times negative 1. And I can, of course, simplify this out. And then 1 plus 0 is 1. 0 plus negative 2 is negative 2. 3 plus 0 is 3. And 0 plus negative 4 is negative 4. And we get our result. Now, again, I'm not going to ask you to do this on the test. I'm not going to ask you to do it in your homework. I just want you to understand that when you see it in the text, that you know where this comes from. Okay, so that's reflections. Pretty simple, pretty straightforward stuff. We will be doing a lot more practice with this stuff on Thursday, so understand that we'll take it a little bit further from here. Let's spend some time talking about rotations. So, is a rotation an isometry? Okay. What would we say? Would we say rotation is an isometry?
Yes.
Yeah, right? We know that our object, the image, if you will, is congruent to our original object, which was our pre-image, so we know it has to be an isometry. Okay, so much like our work with reflections, we're actually going to visit GeoGebra to develop a way to talk about coordinates with rotations. But I do have a couple things that I want to remind you about. First and foremost, when we rotate things, we rotate it about a center of rotation. In the past, this center of rotation has been the origin. It doesn't have to be, though. In fact, we'll look at a quick example of where we would actually translate it from something else. We also have the angle of rotation. Right? The angle of rotation is the angle formed between a ray drawn from the center to the pre-image and a ray drawn from the center to the image, or just the angle that we rotated it. Okay? Nothing really new as far as our explanation of that. All right, let's take a look at how we can do some rotations. So, this time, instead of dealing with just a series of coordinates, let's actually draw an object. Okay? And let's see, I want to delete this one since that was a reflection. And let's see, let's draw a triangle. We got from here to there. And I like drawing triangles this way because it helps us to see that rotation. So, in fact, we should probably make that a little bit taller. It would help us. All right, so we have a series of coordinates here. I'll get rid of that one just for sake of seeing it. A, D, and E. Let's take this and let's rotate it 90 degrees. So we're going to rotate an object. We want to rotate this one. Oh, I need a point, excuse me. There. Now we can rotate. All right, rotate that object on that point. And let's start by rotating it 90 degrees counterclockwise. All right, so obviously we've rotated this 90 degrees. We see that the object has just flipped to its side. Well, let's look here. A was 1, 4. A prime is -4, 1. get rid of that one. Oh, no. Excuse me. There we go. All right. D was 3, 4 and is now negative 4, 3. And E was 2, 1 and is now negative 1, 2. What happened to our coordinates? What happened to them?
They switched and became negative.
All right. Did both of them become negative?
No, the X
Just,
became negative.
just the new X, right? So to rotate it 90 degrees, I'm going to switch my coordinates, and what was the Y now became the X is going to be negative. So let's write these down individually, all right, and we'll come back to it. All right, so if I have a 90-degree rotation, if I have a coordinate XY, that becomes negative YX. Okay? And I will tell you as we go through these, my expectation is you'll have these memorized. I'll tell you that if you, even if you don't have them overtly memorized, a lot of times you can kind of just think through exactly what's happening by just doing a little sketch. Okay? All right, so that's 90-degree rotation. All right, let's take a look at a rotation that's 180. So I'll do the same thing. And 180. All right, we had 1, 4, now negative 1, negative 4. 3, 4, negative 3, negative 4. 2, 1, now negative 2, negative 1. What happened? What did we do?
The coordinates stayed the same, but you just added negative to both numbers.
All right, very good. They didn't change, they just became negative. All right, so we can notate that one. That's excellent. So if we're going to rotate 180, instead of switching, we're just going to negate both of them. So our coordinate xy becomes negative x, negative y. And then let's look, we've got one last one, 270. Okay. And we can kind of think that this is where this is going to go. Obviously, 270 degrees, we've taken the object and rotated it all the way around. We had 1, 4, and we now have 4, negative 1. 3, 4, 4, negative 3. 2, 1 is now 1, negative 2. What happened?
The coordinates split and the Y's became negative.
Excellent. Very good. So, we have that. Now, this was a pretty quick result as far as understanding rotations within our coordinate axes. You can assume that when Descartes set up the system and he started looking at all the things that we could do geometrically within this algebraic system, life had to be pretty easy. It's so nice for us to think about how we can just quickly and easily do something numerically as opposed to having to draw it out the entire time. All right, let's do a quick example. I should probably point this out. These angles we're always talking about in a counterclockwise direction. At this point, we're almost exclusively talking about counterclockwise. All right, let's do this example. So let's say I have these points, and I want to rotate them for the following angles. Okay, so let's go through and do that. For 90 degrees, remember that our coordinates are going to change places, right? So we have y and x, and then one of them is going to come negative. Which one's going to be negative again?
The Y.
Excellent. All right, so A prime is going to be negative 3, negative 2. B prime is going to be negative 2, 1. C prime is going to be negative 1, 0. Okay. And just like that. Okay, let's see here. What about 180 degrees? What's going to happen there?
They're both negative.
And they stay in the same order, right?
Right.
So that's going to be to negative 3, right? V prime will be negative 1, negative 2. And then C prime will be 0, negative 1. And 0 is always 0. And then 270. We know that they're going to switch places. And for 270, the last one becomes negative. Right? So what was our x, right, is our new y. So A prime will be 3, positive 2. B prime is going to be 2, negative 1. And then C prime, should be a colon there, I'm sorry. C prime will be 1, 0. And if we're doing just a regular old reflection, that's all we really need to worry about. We're able to just kind of go through and set it up. Questions on that? Seem pretty straightforward?
Yeah.
I will tell you, and I'm not going to go through it, but I do want to tell you that in the book, you can go through and use a matrix to multiply to get a 90-degree rotation, 180-degree rotation, and a 270-degree rotation. The same kind of rules apply as far as our work within that framework as it did with reflections. I want you to know that it's possible, but it's not something I'm going to ask you to do. So at this point, I'm going to go ahead and skip it. And that is that. Alright. 2 homework assignments should be pretty easy for you. This will be due in 2 days, and we'll go from there.